Good morning, good afternoon, and good evening to everyone. I am Hannah Matthews, and a very warm welcome to all of our participants joining us from across the globe for a very special virtual session in partnership with Beyond Limits. Within the Industry 4.0 paradigm, new powerful technologies are already being deployed towards a smart energy revolution. The driving forces of Industry 4.0, namely artificial intelligence techniques, are continuously evolving, finding numerous applications in modern businesses and organizations. Today's presentation is about the future of AI in energy. Our presenting partner, Beyond Limits, leverages artificial intelligence technologies, develops and delivers cognitive AI solutions that reason, think, learn, and solve problems to assist people in making time-sensitive and mission-critical decisions, most notably supporting unmanned space exploration by NASA. Beyond Limits' proven approach combines numeric AI techniques like machine learning with knowledge-based reasoning to mitigate risk, optimize operations, and increase efficiency. Given the unprecedented circumstances globally, the energy sector has had to make rapid changes to their existing operating models to maintain operations and business continuity. Advanced AI and digitalization strategies bring opportunity for operators to be better positioned for the future by capturing full margins and increasing production from existing assets. Our exceptionally experienced speaker for today, Mr. Chris Clayton, the Functional Product Manager for Process Manufacturing Solutions at Beyond Limits, will share how cognitive AI solutions that have been tested in space can help you get the most out of your complex assets within your plant. During the course of the webinar, if you do have any questions, please share them and they will be answered at the end of the presentation. So over to you, Chris.
Thank you, Hannah. Well, good morning, everyone. Good afternoon, good evening, wherever you are in this part of the world or in your part of the world. We appreciate you joining today and look forward to sharing some information and then hearing your thoughts and questions about what we're proposing and what we're sharing today. In terms of ground rules, just to kind of get us up and running, I'm sure you're all familiar with Zoom, given what we've been dealing with globally these days. So please keep your microphones on mute, at least for the time being. And then when we get into the Q&A, if there are questions that need to be asked, we can then come off mute in order to actually ask questions and have a little bit of a dialogue. As Hannah had mentioned as well, it would be great if you actually have some questions as they come up to put them into the chat feature. We'll aggregate those and then we'll be answering those during the Q&A session near the end. So today's mission, the challenges that we're all confronting in 2020, as Hannah had mentioned, there's numerous. Given the need for changes to our workforce and where we're actually working, some people working remote, a lot of people working remote. It has put a pretty big challenge, in terms of how we deploy our resources and how we utilize them. So we'll talk a little bit at a high level in terms of those challenges, which I don't think we'll have to go too far deep because we all have our own examples of what's happening. We're going to be talking about lessons from space. How do we bring forth solutions, new types of AI and new types of intelligence in order to improve efficiency? So thinking about, what do we take from that experience and from our heritage in the space program and actually use that for, industrial automation and Industry 4.0. We'll be sharing some use case examples more along the lines of how we're applying these techniques so we can make this more of an educational and an informative session as opposed to talking about products per se. So we want to really impart a lot of the knowledge and processes and the way that we're applying our AI in order to solve challenges. And the intention in the upstream examples would be just to show you a variety of ways to do that. And then we'll dive pretty deep into a downstream customer example, where we'll talk about all the techniques that we've shared in the first part of the session here, and show you how they're applied in a very specific way. And we hope that that actually gives you, lots of room for thinking about how these techniques could apply to your world, and we'll explore those during the Q&A. So a little bit of our history, very one slide history here is, as Hannah had mentioned, that we have a deep heritage and a continued collaboration with the Caltech, who's a part of our business, a big part of our business, a part owner in the business as well, and the Jet Propulsion Labs in Southern California, and the work they perform for NASA. All of our technology and IP, and as well as a good portion of our staff, including our Chief Technology Officer, actually comes from the Jet Propulsion Labs and NASA. So everything that we're describing today and working with has either originated there, or has evolved from there, or it was the genesis of some of the technologies we'll be speaking about today and how we apply them. As you had mentioned, Hannah had mentioned, as far as mission critical decisions, how do we get to a place where, how do we trust the decisions we're going to make? A large part of that is coming from this deep heritage in the space program, which I'll talk about in a moment. Everything we're talking about and showing has been validated. These technologies and unique applications of them, which we'll be sharing, they have all been used in a variety of different programs, including the Mars rover exploration missions, and other types of government programs as well. So you can trust that what we're sharing here is grounded in reality. And then lastly, company acceleration. It's been a very, very exciting time for us. Over the past 5 years, we've grown significantly, in large part with a partnership with our one of our largest investors is BP. And they've just been a phenomenal both investor and partner in the evolution of these technologies and the application of them throughout their businesses. So very, very pleased and blessed to actually have such a great partner. We've also, as you can see on the screen, CV Insights, we've been named as one of the top AI companies in 2020, and then Frost & Sullivan Awards in 2019. So we're starting to get that recognition in the market, and as we continue to evolve. So why are we here, and what do we want to talk about? One of the things that you can see here is from McKinsey & Company is just that oil and gas, that there's a $200 billion performance gap, and we'll speak specifically about that gap in the downstream example. And that gap is really in the achievement of, or at least the discussion of, what is your plan? What are we trying to achieve, and how much revenue can we generate? And then realizing that there's a gap in our ability to actually realize that potential. So how do we actually close that gap and take these complex assets, whether they're a single asset or strung together, to complete a process? There's a lot of machinery and a lot of complexity involved here, as everyone on the phone is intimately familiar. So in terms of upstream, production inconsistencies, the ups, the downs of managing these complex environments and making the best decision possible. And, in some cases you may have an accurate geomodel, in other cases you may not. Sometimes there are changes, to your operating conditions that are unplanned or misunderstood. So all of these things contribute to operational inefficiencies, which give us a gap in our performance. And in the downstream, and you can relate this to our participants or people on the phone today that come from other forms of energy, whether it's a utility or a refinery or any other type of manufacturing plant. Think of it as a large-scale asset, and how do we manage those appropriately? The profitability gaps that exist in there, a lot of times it's at least in the case of complex process manufacturing, which we're dealing with, there's a lot of variability in input streams and feedstocks. There's also a lot of complexity in operating these environments because we're doing conversion processes. So everybody on the phone can relate that in some way, shape, or form to what you're dealing with in your own environment. So we'll be giving you some examples of how to leverage these technologies to deal with these complexities and variability in your business that actually is causing some of the disruption to your profit. This comes from Deloitte. As you can see, there's on average, it looks like 40% of the refiners have delivered above average returns over the past 10 years. With 31% negatively disrupted. As everybody has been experiencing with the disruption that is happening in the world with the changing price and the futures and the values that are actually placed on these products, it's quite disruptive, and even more so than when this quote was actually generated. So when we look at what's actually happening in the market, it's even more incumbent upon all of us to actually look for ways to drive costs down and actually achieve these profitability gaps and look to find ways to actually generate as much revenue as possible from these assets. Here's a couple different thoughts, and I have had the joy of actually seeing that these things can be realized in terms of metrics, especially in the downstream in oil and gas. This is from PwC, and it's just talking about how downstream operations and improving your digitization and your utilization of these types of technologies can have huge benefit. So operating costs, especially given the last slide where we're talking about the disruptive nature of what's going on. How do we achieve lower operating costs? These numbers are pretty significant and can have a large impact. Improving your throughput obviously is going to drive more revenue as long as our costs aren't climbing at the same rate. So it's very important to be thinking about the balance of these things, is that we can be reducing costs, but we could also affect our throughput. So how do we balance all of them in unison? And then, plant efficiency. Can we actually drive efficiency to higher levels and, reduce the risks that are related to unplanned shutdowns? Most of what we'll be talking about today is going to be looking at throughput and plant efficiencies and utilizing technologies to get there. The byproduct of that would be dropping some of your operating costs. The unplanned shutdowns is probably subject for another session in the future. So how do we take the technologies that are available to us, and some of the older, more traditional, and some of the more cutting edge things that we're bringing together today, and some of the things that are showing up that can be used tomorrow in your various environments? And really the goal here is thinking about how do we partner with these technologies as opposed to thinking of them coming in, taking things over. These are partnership tools. And I think you'll see that we're very, very clear about the idea of augmentation and support of our people for decision-making. And the goal being, let's max the value out of these complex assets and these processes so that we can generate the profitability we're looking for. So a lot of what we'll talk about today is, operational efficiency, optimizing operations. A big one will be how do we leverage expert knowledge, all the expertise that's in the heads and minds of your people, and especially since there's a lot of people starting to age out of a lot of the complex manufacturing environments that we're all working in. How do we capture that knowledge, leverage it, and make it part of our everyday work so that we can enhance the knowledge and upskill the people that we're working with? Another one that's really important here that I know we always get questions on is how do we increase visibility, but also trust in the systems. Are the algorithms trusted? The alarm states that continually happen, is that alarm real? Do I need to pay attention to it? Especially in a safety environment, it's really important that we trust the information we're receiving. So if an algorithm is producing a change to a set point, or if it's suggesting that an alarm is being raised, can we trust it? And how do we enhance that trust? So we'll be speaking to that quite a bit. And then lastly is how do we identify and then manage or resolve risk, as Hannah had mentioned in the prologue here. So how do we help and support in all this? Well, one of the things that we talked about is how do we leverage what we've learned from the space program and the technologies that we have, and why are they relevant to you? A large part of refining businesses, manufacturing businesses, and almost any business, going back to the assembly line that Henry Ford had put together for cars, is that getting to a place of some level of automation and autonomy gives us an ability to scale, to rapidly develop whatever we're working on. But if we're going to have autonomy, we also have to have trust. So how do we trust it? One of the things that we'll be speaking to in a moment is, when you're leaving Earth and trying to land the Mars rover on a planet that's, a long, long, long way from where we are, without communication, without any, immediacy for rapid communication, because it's a long, long delay in order to get communications back and forth. How do we execute with autonomy and be able to deliver these missions? So a large part of our ability to help you to move towards more autonomous operations comes from the ability to actually navigate foreign spaces without knowledge, without the data and information that you would typically have in order to get there in an autonomous state. And we'll describe that in a moment. And then uncertainty. It's the unknown. What do we do in the midst of the unknown? And when we don't have the data or the information required to make a decision from an analytic or numeric perspective, what do we do with that uncertainty, and how do we actually still act effectively? So dealing with that uncertainty is a big deal and an important part of everything we're doing from a computing perspective. And then, looking at this thing is how do we understand our environment? How do we look at various behavior of our systems and our processes and understand them more readily and more quickly, so that we can move more quickly as a team? Very, very important part of this. Planning and reacting. Plans are great. What do we do in the midst of change? And how do we react to it is a critical part of being successful, especially in our day and age. And now, given in some cases, we're seeing teams working remotely in order to run some complex things. So communications becomes really critical, as well as situational awareness. So jumping into the meat of the matter. When you think about critical decisions and the idea of this journey towards autonomy, how do we get to levels of autonomy and somewhere in between in order to be more productive and yield the profitability we're speaking to? When we're thinking about decisions on that y-axis, and over time, we're looking at improving our ability to move from manual to semi-manual to semi-autonomous to autonomous operations. How do we move in that direction? And in the refining business and large part of manufacturing businesses, there's tons of autonomous operation now. And the reason that they've been autonomous is because they've got a lot of data. A ton of data and a ton of proof where decisions that need to be made are unambiguous. It's a very objective point of view because the data is so rampant and so accurate that we can be confident in a machine making a decision. When you look at a large part of the complex manufacturing processes, there are still areas where human decision making is required. We're still relatively manual and becoming more, semi-autonomous to some degree in certain areas. But it's dependent upon how much data we have. So if you look at the early part of this process and focus on where we are in the manual mode, there's a lot of knowledge about what we need to do and how to operate a certain piece of equipment, how we operate in these processes, whereas the data is actually very, very limited. And as you can see here, this is where uncertainty comes in. The uncertainty is the gap between the amount of data we have and the amount of knowledge we have, right? So using the knowledge to augment the human decision here, to be able to leverage the knowledge and experience of the people who have been with the business for long periods of time, enable us to actually render decisions. So in large part, when we're looking at the journey to autonomy, and we start to incorporate more and more data, and we start to learn more through time, you can see we're increasing this data line, and we start to move more towards a semi-autonomous state. And we're less dependent on knowledge. And as knowledge declines in terms of its necessity for making decisions, we can then become more data-driven. A large part of the businesses that we're working in, including most people on the phone, there are a lot of people who have been digging deep into data-driven solutions that can drive predictive maintenance and drive predictive performance, and looking to get ahead of the curve. And unfortunately, in a lot of the complex environments, the data is still sparse and not necessarily large enough in order to give us that trust and faith that we can make these machine-driven decisions. So we're somewhere in between. The reason that we're bringing all this up, and at least starting this idea of the journey to autonomy, really originates here, is in order to land one of these on a planet a long, long way from home, is that we're starting in an environment where a lot of decisions are going to need to be made by a machine in a foreign land, augmenting that system by a lot of knowledge in order for it to learn as it goes in a environment where we lack the data, and we may see unplanned events and things that come up, and we're going to need to deal with them. So a lot of the technology, as we start talking about this, is really based on the merger of numeric AI and the idea that knowledge and information can be combined in order to help us to navigate unknown or unexpected events. So how does all this come together? From an AI perspective, we want to mimic, and the technologies we'll be describing today, as I mentioned, move from both a numeric perspective and a knowledge perspective. So the ability to sense the world like we do as human beings, what's happening, be able to understand what's going on from a sensory perspective is a critical component of what we do as a human being. It's the same thing what we're doing with technology. How do we understand and sense the world to identify and understand that something is happening that we need to pay attention to? The ability to think and reason, to be able to take that information in and be able to identify it as a set of system behaviors that could be a risk or an opportunity. Being able to actually understand that circumstance and then be able to act upon it is going to be dependent upon our ability to interpret all that information and make the appropriate decision, and then take action on it. So you can see a lot of learning can occur by sitting here and observing this loop of I've now understood something's happening, I've thought about it, I'm reasoning, I've acted upon it. Now, what do we do about that? So we've taken our actions, and there's this continual loop, which everyone here is intimately familiar with. How do we learn from our past performance? So being able to put a learning mechanism in the center of this, so we can learn both from the data and the experience of what we're doing, how we've reasoned about it, what we were thinking, and then what actions and what were the results. So a large part of it, just like we are as human beings, is building a structure and a process for the technologies to actually allow this to occur, both on numeric inputs and our knowledge and our actions. So as you can see here on the left-hand side is, we can be augmenting a person. These can become robots over time when we get enough data to make confident decisions. So this is the basis of it, and where we're going to go now is actually showing you some examples of how to apply this directly in the technology. So getting deeper into how does all this work? On the left-hand side, what we're describing here is a hybrid AI framework, and working from the left-hand side, we're going to be talking more about traditional forms of artificial intelligence and using a lot of what we call the numeric models. So everything that you have in terms of sensor data, it can be image data, text data, location data, demographic data, any forms of data that are necessary for us to actually be able to sense the world, to understand what's happening. Being able to push that down and into our numeric models. So we're making use of the same things that everyone else has. Everybody has a proverbial kitchen of AI capabilities or models in terms of numeric and statistical modeling, neural networks, machine learning, different forms of deep learning, whatever that is from a numeric perspective. It's all part of this plan and part of the framework in order to enable thinking, right? So from a sensing perspective, we've looked at all that data and information, we're consuming it, applying numeric models, but then marrying that to our ability to interpret, to understand, and to be able to leverage the experience of your people, best practices, anything from industry standards and guidelines, being able to bring all that together as expert knowledge and putting that into various forms of reasoning engines or inference engines and the like, in order to combine both your numeric understanding of what's happening to define a particular problem or state of a refinery or whatever we're looking to measure, and then being able to apply reasoning to that. So we sense, we're going to think, and then there's going to be some level of recommendation from this reasoning engine. So at the end of this process, we want to take action. A big part of what we'll be describing today is the ability to actually leverage a lot of different types of techniques for bringing the knowledge and industry guidelines and whatever is necessary in order to interpret what we've learned from sensing, thinking about it, and then applying a rigor in order to come up with significant and meaningful recommendations. So our outputs in that case can be a classification, it can be confidence scores, it's in almost everything we're going to be sharing today, a recommendation. The recommendations, as you can see at the bottom, is going to be also accompanied with an audit trail. So unlike what you've probably seen in neural nets, especially in healthcare environments and risk environments, without an audit trail to actually understand why did a model give me a certain answer, or give us a certain answer, what do we do? And can we trust it? Without an audit trail, in some cases, some environments, we're going to need to actually rely on a human being's assessment and understanding and interpretation of your outputs. So in this world, with this combined AI framework, we have the ability to actually bring that expert knowledge and combine it so that you can actually show the reasoning behind it. And the audit trail now, it can be told. So we've got a way for you to feel more confident and be able to justify anything that a machine is doing to recommend an action. And then lastly, actions are taken by human beings. Everything that we've done and continue to do is all part of being an augmentation and a support in terms of decision support and advanced reasoning in order to support the ability for people to take action. And a big part of this, as I mentioned earlier, is that inner circle. We're going to sense, we're going to think, and we're going to act. So now we've gone through all of this cycle. How do we take that raw data and allow it to continually update and improve upon our ability to act and be successful with what we're doing? So there's a feedback loop in both the data side as well as on the reasoning side. So what rule or what piece of knowledge was actually utilized in order to make a recommendation? Was it successful? Do we need to augment that both on the knowledge side of this equation as well as on the numeric? And both are getting a continuous learning loop here so that we can improve through time. So how does that apply to everybody on the phone? That was the foundation of the technologies, and what we wanted you to kind of walk away with today is that there are more than numeric ways to just to solve the problems that you're confronted with today. It's a combination of these two that can actually help us when data is a little bit sparse. How do we augment that? When data is sparse, can we still take action? Can we still make recommendations occur? Can we still move the ball forward and achieve stronger, more efficient operations? So how does that apply in energy? What you're seeing here are a variety of different areas that we've applied the techniques we just described. And, it's been in the upstream where, characterizing a reservoir, where to drill, why, when. Well planning has been a interesting exploration for us, infill wells, well health management, being able to actually understand the dynamics and changing environments that we're dealing with, and how do we manage an asset and extend its life or protect its life from degradation. Some things in the midstream are more like supply chain, being able to understand the flow of information, the flow of assets, and tracking them throughout the world, and being able to actually understand their impact so that we can better plan the entire supply chain. What we'll be speaking about a lot today is really on the downstream. It's going to be the operations advisor, and how that system and approach, leveraging everything we just shared, can be applied to drive value, efficiency, and profitability. So starting with an upstream example, this is going to be at a higher level, but we'll give you a good sense of it for anybody on the phone that's actually working in the upstream. My particular focus is on downstream and in manufacturing, in process manufacturing. So a lot of what we're doing in the downstream is the same application of what we're doing in the upstream, in terms of bringing the numerics and the symbolic methods together so that we can improve efficiency and profitability, and drive things forward. So I just saw that the poll popped up, and I'll give everybody a second here to answer those. I'll take a little pause here. So thank you for answering the poll. Hopefully you had a minute to pause and answer those questions. That'd be helpful for driving some of our conversation as well. So as an example, this is hybrid AI to assist field planning. So, where do we drill? When? How is that a higher probability than another? Can we get there quicker? As you can see here with the statement above, is that by applying this approach, one of the things that's critical is, can we give you a recommendation and a strategy, and do it in a quicker time frame? So when you're trying to move quickly to access an asset, or improve upon our ability to access and capitalize on that asset, can we do it faster? One of the things that we've seen by applying this approach is, with limited resources, can we actually get more out of our resources, in this case being our people? How do we take all of this vast information and be able to condense it down and simplify it from a process perspective, so that we can consume as much data as possible, but yet do it in a way that cuts this cumbersome process for combining all this data and information to come up with a strategy. So basically what we're describing here is that taking the domain of knowledge and being able to add a lot of characterization to it, and make that knowledge base accessible and leverageable within a hybrid model. And once that's done, you're also going to see that the system is going to create the network. It creates a network of time distance vectors for this reservoir. So it's literally building a graph. And from that graph, it's actually looking at what are we trying to do, by when, what is our goal, our end state, and being able to actually then pull this together and reason over it, so that we can make better decisions about when, where, and why we should look at new locations. So the reasoner is actually looking at things like, I have a quality requirement, or it's a time requirement, time to asset, asset acquisition, and being able to actually perform at a certain quality level at the same time. So where and when becomes an important ingredient here. So the reasoner is looking at all of these different types of goals or reasons by which you're attempting to leverage this asset. So by combining all of those and running them in sequence, we're going to come up with this drilling recommendation. So we can vastly shrink that process down, because the reasoner is going to be looking at, if we're looking at quality and there's a trade-off decision between quality and location, now the reasoner is actually looking for the best opportunity for marrying the attributes of what we've seen, distance to aquifer as an example, or accessibility to long-term energy, right? So if we're looking at it from varying degrees, how do we marry and come up with the best determination? So there's a lot of permutations and combinations of potential answers, and in this case, the reasoner has given us the ability to bring all of that together. How do we advance that? A lot of the questions we get, can we use simulation models, and how do we integrate with those? And can we use machine learning models that you may have come up with? And how do we take these hybrid models and bring them together? So the answer is it can be done, and it gets done quite a bit. So, being able to actually integrate simulation models into what we do in terms of a traditional numeric model, bringing it together with a reasoner and some of the graphing concepts and approaches we're using from a data perspective, enable us to build some context so that we can then use simulation models that you may have on hand, or things that we need to interact with, and plug them in. So in these cases, if we look at the number of parameters, as you can see here, as I mentioned earlier, permutations, the number of permutations that need to be run in order to come up with an answer with simulation can be quite impractical. And the runtimes can be extremely long, as everyone knows. So from that perspective, how can we help? By leveraging knowledge and using the reasoner, as I mentioned on the previous slides, we can actually reduce the size and space of the data sets. And in this case, as you can see, it's using the term of intelligent sampling. Can we actually produce a data set that can be used by the simulation model in order to test some of our concepts? So as you can see here, by using the reasoner in the midst of your traditional processes, we can actually then prune your data sets and simplify the amount of data that you're consuming in order to then more quickly get to the answers you're looking for. And through time, as we become more and more accurate, the characterization that is coming from the use of the reasoner, we can actually then see that we're labeling things maybe a little bit differently. And we come up with, as you can see, meta models. And these meta models, as we're testing them, become popular or become successful because of the, or I should say, they've been successful in terms of the result that you're getting. We can then reuse those and further refine them. So each of these meta models can then be reused continuously. So as I mentioned in those previous slides, both the knowledge assets are improving as well as your numerics. So in this case, you can actually see we're improving through time. A big piece of that, as I mentioned earlier, is just this last one, is that if you're running neural nets and you've got your simulation models, being able to actually give them what they need and the context of the situation that we're looking to solve for, as I mentioned, quality or specific location, or if there's a time orientation about when we want to execute on the plan to drill or expand our operations, then these are all the attributes by which the reasoner can then reduce the size and scale of the data that's looking at by looking at just what's necessary. So it significantly truncates that process. and hence optimizes your operation. So going out of the upstream and more down into a specific example for downstream operations. And for everybody on the phone who's actually inside of power plants or other types of manufacturing environments, a lot of what we're describing here is basically very, very leverageable. So, it's a highly complex processing environment. In refinery world, this particular client was looking to improve the operational efficiency and realize tight margins. For any hour, day, if you're running off plan in terms of profitability targets and you're seeking to achieve specific targets on a unit by unit basis across the entire refinery, then reaching that margin goal is critical. And for every minute, day, or hour we're running off of plan, it can cost us. So the challenges you're seeing here are based on as I mentioned, profitability gap. So the planning objective for what were our targets and what were the dollar by dollar or barrel by barrel expectation in terms of profitability. It's how do we close that gap? Because there is a gap between the plan and the actual performance. And the solution we'll be describing today actually seeks to operate to the plan objectives and enhance our ability to actually close that gap. Another thing that it's a bigger challenge is each of the refiners across the globe have been, a large number of refiners across the globe are looking to become what is called feedstock advantaged, be able to consume not just one type of crude slate. In some cases, more than just crude. You could be a hybrid plant consuming other inputs other than oil. And some of you may already be doing that. So as the variability of the feedstocks has increased, obviously we're going to have a lot more variability in our downstream processing of that raw feedstock. So as that occurs, then we're also seeing process upsets. So we're set up to consume a specific grade of oil as an example. And as that specific grade of oil shows up, it's not what we thought it would be, or it could be that and our system and equipment is degrading at the same time. So we're seeing varying in performance, and yet we still have a goal, a profitability goal to achieve. So how do we rectify that? How do we more quickly answer that call? How do we modify our current operation in order to still achieve that profitability goal given the variability? So the last part here is time to decision. In some cases, we've seen and have heard that achieving some of these plans can take days for getting the operation to actually start to achieve the plan objectives. So how do we make that time to decision process much more truncated? Right now it can be slow, sometimes it's fast, but on average the time to decision is a problem. How do we get people, when there's a need to override a controlled system and process, how do they understand the domain, understand the problem, and be able to quickly rectify it? So as an example, to bring this all home, the refining optimization model. So how people are typically running optimization inside of the manufacturing processes in a refinery, we've seen is, you're going to be setting longer term plans in planning and scheduling. There's a thing called the LP model. For everyone in oil and gas, you'll understand this. Manufacturing, there may be a different type of optimization model being used, but you're looking forward. How do I consume my assets and produce a result? In between all this is a layer of operations personnel, and their job is to actually manage this process, keep it safe first and foremost, and then achieve profitability as a secondary goal. As that process is employed, you've got this model saying, here's what we want to do to achieve profitability. The systems are configured, whether it's through a DMC or a DCS or any other form of control systems, that configurations and targets are pushed down and automated control systems are put in place. Most people on the phone And most of the people we talk to say, yeah, we have all these things in place, and they're working beautifully. What we're in business to work on is this profitability gap. There's a gap in the profitability because the DMCs, the control systems, are achieving 85 or 95% of the goal, but we're leaving money on the table. There's an operational gap here in terms of the ability to manage the systems and put them back into a operational state. Most of what you're seeing here in this middle process is an interpretation of this plan. There's an operational plan put in place, and you have a lot of people, which we call the human decision loop, interpreting the information given to them, looking at what's happening when there's a problem that it occurs. There's a lot of knowledge and expertise that needs to be imparted or at least understood in order to resolve the problem. What we're looking here is how do we take that expert knowledge and information and embed it in a workflow in order to take what was typically a manual process and be able to both sense it, think about it, reason on it, and be able to recommend a solution so that we can more quickly take changes that are occurring where you look at the control system, and down here in the control loop, we're off plan. There are parts of this process that need to be rectified in order to get us back onto plan. How do we do that as quickly as possible? Right now, the human loop, for the most part in refineries, is left to documentation, conversations, and a lot of interactions with other people for complex problems to be solved. So what we're imparting here in the refinery is employing an optimization strategy where the advisor that we're putting in place, in this case, a shift optimization advisor, is employing the reasoner we just talked about in some of the previous slides. It's applying a lot of the cognitive technologies that we have, including some of the numerics that we mentioned. And what's essentially happening now is we've digitized the manual process. We're taking the knowledge and expertise of the business and its best practices and embedding that directly into a reasoning system in order to enable these process engineers and operators at the control level to now identify when a problem occurs. The engine itself is seeking a solution. It's looking at all the permutations and combinations of potential solutions in order to solve the problem. It's using the numerics, combining them with this knowledge, and being able to then apply our best practices and standards of practice in order to enable this human decision loop to operate much more quickly. And in this case, the analogy we give is that this type of hybrid system enables us to support this human decision loop in the same way that a distributed control system can support the control loop. These are two separate systems. As you can see below, you're at a control loop is a closed loop system. Our system is operating in a separate external system, and it enables the operator to quickly get to what's wrong, how to fix it, and provides the recommendation as well as the audit trail as to why this recommendation has been given. So at this case, once we've got an answer, the operator makes that change, and we're going to improve through time. So from a structural perspective, putting this together, as you saw in the previous slides, it's like we referenced the numerics and the symbolic and all the different types of things that come together to enable thinking and reasoning. We've encapsulated that into a structure which allows us to plan. So again, knowledge, assets, and structure. How do we plan the operation? So in this case, when you're setting a plan, they're going to launch an operational or a game plan of sorts to establish how to run the environment. Inside of that, we're going to prioritize what constraints we're looking to run to, or how do we prioritize what would be the next best action, and looking at what types of actions are going to be most appropriate under what conditions, and being able to establish all of that as part of a planning construct that can be leveraged through time. And then on the operating side of it is giving the operator, you know, automatically identifying the problem, giving them the solution and the recommendations so they can act on it. So when human action is required, the system is automatically giving them what they need. The human being's always in the loop. Excuse me. And they would ultimately be the person who will affect change at the controls level. And at the end of the day, this system itself is going to be really the system of record, so that when we complete this loop from planning to operating and back up here to improve, how do we leverage all that information? So over a span of a year, you could have 50 or more plans and all of the operations that were performed, so that we can actually see, was it effective? Were the recommendations effective? Essentially, we've digitized and historized all of your planning and recommendations, and now we can actually learn from both the human action and the data in the system. To tie this all together based on what we talked about previously is, you know, the concept of a use case is based on production optimization, and how do we optimize that performance? In this case, from a sensing perspective, we're looking at all the subsystems and sensors from a PI data source, managing temperature, pressure, all different types of data, humidity, external temperature, and then, you know, what do we do with all that? So reasoning over it or thinking about it is classifying when are we on or off plan, leveraging all that best practices, and then first principles and physics models can be incorporated here as well in order to help with these decisioning processes and producing a recommendation for the advisor. So it ends with basically a business impact where we really are looking at improving profitability, time to decision, leveraging and extending expert knowledge. So we've embedded that expert knowledge directly into the work process. And ultimately, we're looking at efficiency gains that, just like we showed in the earlier slides, it could be 10% or more. In many cases, the people who are actually consuming, or refineries consuming, heavier feedstocks, which are lower cost, can yield a higher margin. Can we do those efficiently at the same time, consume heavier oils, and at the same time produce efficiency? So with that, I apologize, I probably ran a little long. It's a lot to cover today. From a Q&A perspective, we've got a few minutes left. I would love to hear from the audience in terms of any questions and thoughts on what we've shared today.
So Chris, it does look like we have about 4 questions that were asked in the Q&A section. Mm-hmm. So I can start with the first one from Saeed. Data is not knowledge. The knowledge will have to increase as data is analyzed. Decisions will always be based on knowledge, not only data. Would you elaborate on your views about data-driven decisions?
Yes. It's a good clarification. So thinking about control systems in many cases, as an example, data, in those cases, you're looking at systems where we're consuming just data, and it's only data. Those types of decisions that pose minimal to no risk, obviously, have already been automated out. So it's purely a data-driven decision. In other cases, where a decision is going to have an impact, potentially not just on profitability, but on safety. Obviously, it's an issue. If we're working with combustible assets like these, then the knowledge on safety, the knowledge of best practices, and those types of things are also brought into account. If we're going to resolve a particular issue by increasing temperature, but yet if we increase temperature to a certain degree, we may have a catastrophic event. That's a big difference. So it's the distinguishing between those two is the knowledge of the past, and using that knowledge in order to inform a particular decision is part of that. So I'm hoping that answers that question, because it's really the distinguishing factor between those two would be, you know, along those lines.
Thanks, Chris. The next question, there's 3 more. The next one's from Joseph. Is there any use case where the act is also done by machine instead of human?
I'm certain there are. In our world, we've yet to do that because the variability and complexity of the things that we're managing would need a lot of proof through time where we've gotten to a place where the decision or the recommendation would pose zero risk. There are areas where we could theoretically apply these things, and the goal would be that these types of human loop automation for decision making could get to a place where the act portion can be automated. It is doable. It just depends on the use case. In the cases we're describing here, if our answer gets to a place of 99.9999% accurate in terms of its recommendation and the action was taken as given, and it poses zero risk, then theoretically you could close that loop and that act portion could be machine driven. So it would just depend on the use case, in terms of regulatory or safety issues.
Thanks, Chris. The next question is from Rakesh. Will we be dependent on your team to manage and update the Refinery Operations Advisor?
No. One of the unique aspects of what we've actually created for that particular solution, it's designed to be managed by the experts. So once implemented and the information and the structure is in place, optimization engineers can actually write the plans, they produce the plans, they establish the setup and configuration of the system on an ongoing basis, and any changes and updating to what goes into the system in order to run it is actually designed to be managed and continually upgraded, or I should say updated, by the user team. Anything in terms of the underlying structures that run it in terms of data and data structures or data inputs, most of the data inputs, if they follow the same model that we have, you can add even new sensors, you could add new assets, you can take the system and it's configured, for example, for a NAFTA system. You could take it and configure it to run on an FCC unit or a coking unit. So it's meant to be fully extensible in order to support a lot of different types of environments that you're looking to operate to a plan objective. So implement a plan and operate to it. So it is wholly built for customization and utilization by end users.
Thanks, Chris. The next question is from Terry. Have you speculated on how your tools might be applied to managing a distributed energy grid?
Yes, that's an interesting question. It actually rose, there's several things that are similar in terms of distribution. That would be a conversation we would love to have in more detail. There's several historical projects we did for oil and gas where these types of distributed networks have different goals and objectives, and how do we manage the on-ramps and off-ramps, and how do you make the decisions in order to, the appropriate decisions. So there's a lot of decisions that, trade-offs that need to occur at each of the different on-ramps and off-ramps in that network. And there's some very interesting ways to apply this to that, to facilitate faster, better decision-making at each of the intersections. It can be applied, and it's a very intriguing use case for us. So we'd enjoy talking about that in further detail.
Thanks, Chris. It looks like a few more questions have come in, so I'll keep going. The next is a follow-up question from Saeed. Thanks for the presentation. Can you provide actual examples that demonstrate business impact and ROI, and how much was that?
The last use case that we're describing actually is based in exactly that. So looking at efficiency through a period of time, how do we measure our efficiency improvements? So the ability to actually deliver on a plan is actually what that use case is based on. So from a planning perspective, you're looking to achieve a specific margin through a period of time, which would be a given plan or a campaign that you're running. So it's a 2-week configuration of your environment, and you had specific objectives that need to be met. Now, if you were to compare those from plan to plan, are we seeing a market improvement based on the efficiency gains? And the efficiency gain in this case is the ability to actually move closer to your plan objectives. So are we moving 10%, 15% or greater in terms of closing that gap? So the efficiency is going to be measured in our ability to actually return to our plan objective through a span. So the use case we're describing there for the refinery is based on that principle. So continually improving our efficiency increases our throughput, which drives profitability. That's basically what that last use case was actually describing, is a 10% increase in our ability to efficiently operate closer to plan. And then when you marry it to feedstock utilization, there's also a gain there in terms of the differential or the crack spread between the different feedstocks that you are consuming. So if we're consuming lower cost feedstocks at the same time, we're actually improving efficiency. That's the net gain there.
Thanks, Chris. The next question. What can you do to overcome the need for high data for developing reliable AI? Also, security of big data transfer.
What was the first part of that again? Because I got caught on the last part there.
What can you do to overcome the need for high data for developing reliable AI?
Yeah, so that's a great question for what we just described, is that when data is sparse or data is not trusted, so in some cases censor drift occurs, or we're missing data and we need that data for a model to run. So if your models for defining, let's just say you're using models to predict off-plan behavior. So you're using models to actually a machine learning model, and you're predicting throughput or performance by a particular unit. Say it's a NAFTA unit inside the refinery, and your prediction model is less than accurate, and we're struggling with it. But obviously it's an important piece. In order to augment that, what we're doing is the symbolic layer comes into play, and it's the ability to actually still make relevant decisions, be able to advance the art of running the business, even when some of the algorithms may not be as productive, or as accurate as we would like them to be. Another, I guess, a more accurate use case for that too could be, when you're trying to predict an asset performance or predict asset failure, and the model requires a ton of data in order to get there. There are heuristic types of ways for identifying problems with a piece of equipment, which a hybrid model like this can actually be very useful. So as an example, looking at the towers that are on the screen here, you have a drone that's flying around, and your models for predicting whether any of these things are degrading isn't as effective as it should be, or you're just getting your confidence in that model is very low. Getting more data may not be the answer. A hybrid model in this case could be using visual interpretation of imagery, and being able to then say, from an expert's perspective, say, yeah, this system's degrading faster than we think, and here's why. The augmentation of that type of model with this kind of hybrid model based on visual imagery and the interpretation of it can enhance your ability to still take action, even if the model is deficient. Another way when data is not large, the example we gave earlier is, in the hybrid modeling for field planning, is using AI in order to identify, or I should say the symbolic layer to actually identify or prune large data sets in order to identify the data you actually need. So you can actually use the two in combination to actually improve your ability to isolate data and variables of interest in order to accelerate that. It's a big question. And then from a safety perspective, that's a whole nother animal. And that's something that I probably wouldn't answer on this call. It's too big of a question. If you've got a follow-on question for that, I could probably have someone answer that, as a follow-up.
Thank you, Chris. The next question is from Abdul. What is a typical methodology to implement, and which unit should be selected to start with in a refinery complex? Any case studies to share with? Thanks.
That's a great one. We get that all the time because it's really important to, everybody wants to get to operational efficiency. Everybody wants to get there, but there's limited dollars. And how do we choose effectively? So a good place to start, which it's been the last 3 or 4 days, I've had quite a bit of that. So I'm actually looking at a notepad that actually has those questions on it. So we have a criteria that's really based on the idea that where is the variability the highest? And variability would be picking a unit where there's a lot of input streams, and different characteristics of those streams that are feeding a unit. So, and as an example, a typical starting point would be high value unit, such as a catalytic cracker. And looking at where the complexity of that unit and the value of that unit for creating light ends, being able to transform a variety of streams and being able to turn them into higher value products, right? So the economic viability is one. Dynamism inside of that system that is, it's quite dynamic and just, can be difficult to manage. The complexity of the unit is important as well. Simple things where it's one input, few outputs, with minimal amount of heavy knowledge required in order to solve any upsets. That would be a place not to start. To start, we want to look at that heavily variable system where there's a lot of variability or dynamism, where the complexity is such that expertise and collaboration between different people in cross-unit type of thing, where the feed might be from a preceding unit, or the solution may be in a unit downstream. So how do we create that level of collaboration? So we want to look at something that's in the center and has the 3 things of complexity, dynamism, and value to the organization. And if the clincher for this would be, if your plan is continually not being met, you have an objective that you need to meet, how do we manage to that objective? This is a layer that would actually enhance your ability to deliver to that plan objective. So
Thanks, Chris.
Sure.
A couple more questions. So the next one, what level of digitalization is required for AI, like a refinery constructed 25 years back?
The most critical piece of it is sensors, and having enough sensors throughout the infrastructure in order to capture the variables that are relevant and important for change. So if variable feedstocks are coming down and they're much heavier than what we've set up for, and maybe we don't have enough tankage and we're having a struggle with blending anything in order to solve it. So how do we adapt in that moment? So as these things are occurring, how do we adapt to some of those types of challenges? And it's not not all that easy. I kind of lost my thread there for a second. Could you replay that one just for a second, Ashley? I want to make sure I answer the question because it led to another answer.
Sure. What level of digitization is required for AI, like Refinery constructed 25 years back?
Yes, thank you. So a lot of the, regardless of the age of the refinery, and some of the refineries we're in, they're very, very old, but they've been adapted with the sensors. So that's where I was going, is that in order to actually even affect change inside the system, we have to understand the dynamics of it, and what are the essential things that we need to monitor, and then what do we need to adjust. And if we've got sufficient data on monitoring the situation so we can understand our behavior of on or off plan from an objectives perspective, then that's the first piece. So digitizing that data, and typically in manufacturing environments, especially in refining, the PI data from the PI systems is typically enough. And if that data can be streamed, we consume that streamed data. So that would be the first place to start, and getting at least enough data so you can understand flows, temperature, pressure, assays on the quality of your streams, all of those things, including external conditions, temperature, weather. These are all the normal types of things you want to take a look at.
Thank you, Chris. And a follow-up question from Banu, who had asked that first question. Can you distinguish gains delta between hydro, skimming, and full conversion? Likely payback period.
That would be a level of detail probably for someone on our team, more on the domain side of things. Hydro skimming versus, what was the other?
Hydro skimming and full conversion.
So theoretically, as part of the system right now, that isn't something that we're doing per se. It is entirely doable, mainly because it's just being able to measure what your expected were versus your actuals, and then being able to look at the differentials between those two, and modeling to it. We're currently in the current iteration of the advisor that we have for refining that isn't being done. However, what you're describing is possible should it be a use case you wanted to explore.
Okay, thank you. Two more questions. The next from Abdul. What is the difference between digitization and AI?
Well, there's a bunch of different things. I guess digitization, from the way that I've heard it defined, is really getting your assets and your data in order. Digitization is ensuring that we've got data on all of our assets, and being able to get that into a form and a structure, and enabling it, right? So we can access all of the elements of our environment from a data perspective. Digitalization is another, I didn't even know that was a word until it was probably coined by the consultants, but digitalization is the enablement of that data. So can we put it into a process? So in the example that we just had with refining, having the data is one thing, but being able to actually process it, put it into a form and a structure, and making it possible to be transported and utilized in both a safe manner, so that it's secure, actually from a security perspective, and then enabling a person to consume it. So building the necessary APIs or the access routes to get data in and out. So digitizing it's one way. Digitalization is making it possible, and then moving towards utilization of that would be the AI. So like the APIs would plug into our systems, which now we're going to consume that data. So it's kind of a journey from digitization to digitalizing it, so that it's a process that's continuous and we can trust it, and the flow is there, the pipes are in, and now we bolt that on to the system. Now the intelligence systems can now leverage those assets and make use of them. So it's typically the journey in a simplified view.
Thank you, Chris. The next question, what do you think about applying synthetic data from simulation models for learning AI?
I mean, it's a good idea. It's you know, any way that we can actually train systems, the better, and being able to actually exercise them and you know, evolve them. It's you know, in many cases people are doing that. You know, it's data is a tough one. It's you got to have data in order to you know, evolve and do your own R&D. So you know, it's just one of the many ways to enhance the amount of information, or at least data, that we can feed to these systems. So yeah, I think one of our data scientists would be better at answering that question more fully, but yeah, I've definitely seen that done. I know we've explored quite a bit of synthetic sets and building our own you know, data sets in order to you know, test different hypotheses and things.
Thank you, Chris. And yes, we can take some of these questions back to our team to get more complete answers if necessary for anyone.
Yeah.
The following is a follow-up question from Abdul. Kindly share some typical case studies so that some business cases can be worked out by optimization engineers.
So it's a great question, because you know, one of the things try to reduce the question. I need my own symbolic layer for this one to reduce the amount of answers I could give for that one. A good example of this would be our system is tracking mitigation actions, like what action could you take, what's available to be taken. We also measure things like what action is not available. So you may have 20 or 30 different possible, you say it's a 50 or 60 possible ways to solve a particular problem inside of a unit, right? So the plan is set, and we have an outcome objective for throughput or quality of product through you know, the NAFTA system as an example. And you're looking at that, and we're clearly not achieving it, and it's been difficult to achieve for the duration of a plan or a period of time. Well, the data that comes out of our system, first off, the plan was written by an optimization engineer. The plan is being enacted by teams inside the refinery. Now, what data can we get back to that operational engineer or optimization engineer? So when a NAFTA system in this example is underachieving according to its goal, we've got a lot of data, and inside of that would be the inability to take maybe 50 or 60 different handles that could have been pulled, and consistently we're seeing that none of them are available. They can't be pulled. So there's a plan problem or a flaw in the systems themselves, right? So in this case, if the plan can't be met and it's consistently happening, then this is feedback, and it's information and data that can be fed back that actually says that the types of these types of scenarios, your plan can't be achieved. So it adapts their thinking, and it can actually adjust. So when we talked about historizing these plans, you have a strategy for running the environment. We've run the strategy through. We've seen that the operation and all of these constructs, the engine can't solve the problem. It's run through all the possible combinations and permutations and says you can't you know, achieve the threshold, or at least the goal that you're trying to achieve with this unit for that period of time. That feedback loop now helps the optimization engineer to adapt future plans. Part of what our system is also going to do is when they go to write that next plan to run the environment, we can suggest you know, a plan construct that's going to be more conducive to the current operational state of the refinery. So in that case, your optimization engineer can actually adapt their plan before they even push it out into the wild for operations, you know, in order to develop an effective plan.
Thank you, Chris. And it looks like we have our final question, unless any others pop up. This is a follow-up from Banu. Basically, I want AI economic impact on a refinery without FCC and with FCC. You can share for a crude unit alone with AI value addition. Thanks.
Given that we're at the end of our time, that one's a big question. I'd probably take that one offline. It's there's a lot there. You know, and it with an FCC or without one, that's a big component of change. You know, and the question would be very large. Definitely a valuable question, but yeah, one that would require some thinking and maybe even some dialogue on it.
Thank you, Chris. So that ends the Q&A. I believe that we have run up on our time. So thank you to everyone for joining. Thank you, Chris, for speaking.
Yes, thank you. Thank you, everyone.